Yeah, the next topic that we are going to talk about are binary trees. A binary tree is a finite set of nodes that is either empty or consists of a root and two disjoint binary trees called the left and right subtrees, each of which may also be empty. A binary tree is a non-linear ADT, just like the tree, or a hierarchical ADT as opposed to a list or a stack or a queue that arrange the data in a sequential manner. A clear hierarchy among the nodes. Compared to a general tree, the binary tree consists of only two children. So it warrants a separate ADT. And basically what we're saying is I can represent the tree with exactly two pointers. Remember when we talked about representing any arbitrary tree, we said we should have an array of linked lists. Here we could represent by two different linked lists in every node. Okay, so again, redefining the various parts. Access it's hierarchical because access to any node in the tree, just like any regular tree, is via the root node. And these are leaf nodes which do not have any children. And these are called internal nodes. Just like in the regular tree, a root can also need not necessarily be an internal node because sometimes it need not have any children at all. So when you look at binary trees, this is a complete and a full binary tree. It has a left child and a right child. This is a skewed binary tree. And this is a full and balanced binary tree. It's also called a perfect binary tree because the left side and the right side have the same number of nodes. Now, full and complete binary trees have some very interesting applications. And what is a full binary tree? Every internal node has two children in the full binary tree. So this is called a full binary tree. And this is neither complete nor full because it has the right child only and doesn't have a left child. This one, for example, is complete, but it's not full. What does it mean here? When we take this particular tree, we start filling it from the left side, okay? And if at all, the last child may be empty, okay? What I mean is we can't take this node, put it over here. That would not, what I mean by this is the following, that, okay, I cannot have a node here and not have these nodes. Suppose these nodes were not there, then that is not a, that is not a, sorry, let's say I had another node here, 2, and no node here. This would not be this would be a full binary tree, but not a complete binary tree. I hope I'm clear with what I'm talking about. So this is the important point about complete and full binary trees, and we will see some nice applications of all of them. Okay, what are the operations that we perform? So you have a binary tree node with a left child and a right child and a root node. So I can create a binary tree with a left child and right child as children and V as a root. So what is V as a root now? It will be your element type and returns the tree rooted at V. I can create an empty binary tree. I can find a parent of a tree rooted at N. I can find a left child of N, of the tree at N. I can find the right child of the tree at N. Then I can also get the root of the binary tree. What I mean by this is I can get the entire binary tree, which is rooted at some node, let's say B. Okay. Now there are some properties of binary trees. I'd like to look at full binary trees, and these are some very interesting properties. We'll try to prove some of these properties in a little while. If T has I internal nodes, the number of leaves is L equals I plus 1. We'll see why this happens. Let's go back and look at this. This is a full binary tree. So how many internal nodes are there? 1, 2, and 3. Therefore, the number of leaves is 4 here. And there are other properties. The number of nodes in the tree is 2 into I plus 2I plus 1. We'll get back and look at this. So number of internal nodes are 3, therefore 2I plus 1. So what we will do is we'll look at some of these properties and we'll try to prove some of them. And so obviously this follows from here. We'll repeat this in a little while. I'll use my, we'll go through my notes on proving this. There are many applications of binary trees, representations of sets, Huffman coding, heaps and dictionaries, and each one will use a different kind of a binary tree. And for example, for dictionaries, it will use a binary search tree. Heaps use what is called a priority queue. This will use a forest of binary trees, and representation of sets, you will represent it as binary trees with some order in them if you wish. Okay.